For today's talk, let me introduce Dr. Zack Spica. Zack received his bachelor's and master's degrees in earth science from the University of Brussels in Belgium, and his PhD in geophysics at National Autonomous University of Mexico in 2015, where he graduated with highest honors and the congratulations of the jury. Zack started his postdoctoral work at Stanford University. After that, he got a researcher position at the University of Tokyo, and currently he's working for the University of Michigan in the Department of Earth and Environmental Sciences as an assistant professor. Zack found his research interest in understanding the interior of the Earth at every scale using seismic data, and particularly he is conducting research about volcanic and hydrothermal systems and predicting ground motion caused by earthquakes. In the last few years, he has been working actively on distributed acoustic sensing systems, which is the subject of today's talk. So without further ado, I would like to give the word to Dr. Spica.
Thank you, Marco. And thank you everyone for being there and for inviting me today. So in the last few years, I've been involved in fiber optic sensing technology. When I was at Stanford, the University of Stanford, actually during the last year, Stanford was operating one of the first fiber optic network. And so that's how I got involved and then into a postdoc in Japan. And they also had ocean bottom fiber optic. And that's where I really realized the potential of ocean bottom fiber optic as a new frontier for seismology. So today, what I'm going to discuss, I'm going to show you this SPIN network. You told me you try to monitoring the Earth or the vibrating Earth or the living Earth using different techniques. And here I won't go into many details, but I will try to give you the breadth of the possibilities that fiber optic at the ocean bottom can provide for monitoring applications. So if you have more technical question, maybe at the end, but probably I would try to be relatively shallow during the talk. So as you know, most of the earthquake happened at the plate boundaries. And actually most of the largest earthquake, they happen offshore, where in the subduction zone. And if you look at our instrumentation, and here on this GIF, you see the evolution of the seismometers networks since the 70s with the little triangles. Well, it's 99% of our sensors are inland and not offshore. We have a few clusters here around Hawaii and other specific spot. And in general, what happened is that these offshore network, they are not permanent. It's very rare to have permanent network. And so there is a very big lack of observation of seismicity offshore. And one thing also to recognize is that offshore seismology or ocean bottom seismology is probably one of the most expensive operation in solid earth science. Because every time you want to install just one sensor, you need to go out at sea with a dedicated vessel and a dedicated crew full of scientists, trained scientists. And so it can, the price of just installing one sensor can be very high. And on top of that, as I said, some sensor, it's hard to maintain them for long term monitoring at the bottom of the ocean. So you have one of the last development was these mermaid sensors that basically are kind of autonomous sensor, and every time there is a triggered earthquake, the sensor can go up to the surface, send the signal back to the land station, and then sink down to the bottom of the ocean again. And there is another way to have continuous monitoring of the ocean bottom is using cables arrays or cable ocean bottom seismometers array. And for this, Japan is definitely leading the way with this technology, with the installation of DoNet 1 and 2 and the famous SNet network. That's basically what you have. So it's a cable, a fiber optic cable actually, that is connected to these what we call repeaters. And inside these boxes, where the fiber, the signal, the laser signal for telecommunication can be amplified, but also there is like an accelerometer or a seismometer in these little boxes. And so you have like a few landing stations, and you have like almost real-time communication with all these sensors connected, installed at the bottom of the ocean. But this is like probably several billions of dollars to install such networks. Japan is definitely leading the way in this. And then there is also this fiber optic sensing technology, DAS, which in fact you can use the fiber I just showed you from SNet, for example, or other fiber from telecommunication, and analyze the axial strain along the fiber. And so how does it work? If you have like a pulse of light, and here like you have a piece of PVC, and you see, so the light is reverberated inside this tube, and the attenuation is relatively low, but yet there are also little impurities that we call scatters, and so there is a portion of the light that comes back to the laser, right? So you see here at the entry, so there is like some light that is reflected back, okay? And so what the DAS does, in this case, it will measure how for one given pulse of light, it will send another one right after and see if there is any phase shift between these two. And you know the speed of light, you know the length of your fiber, and so you can interrogate this phase shift, or you can interrogate how the light is coming back to your interrogator at a very high sampling rate. And the thing is that this phase shift is proportional to the axial strain along the fiber. And what's important here in this equation really is, so phi here is the phase, and GL is the gauge length, which is basically the length over which this phase shift is averaged. No? So we do not measure axial strain on a point along the fiber, but over a gauge length over distance. So it's kind of an integrated measurements of the strain at several positions along the fiber. And one thing which is really nice with DAS is, as soon as you have one fiber installed, well, you just install this DAS interrogator, and you can interrogate the fiber at a very high spatial sampling, like of the order of 1 meter. So every meter, because you know the speed of light, you can interrogate what is the phase shift along the cable. And for who like to do field work with DAS, field work in general, sorry, I'm sorry, but field work with DAS is actually extremely boring. It's so here you have like a DAS interrogator, how it looks like. You go in a data center where you have this cable that here it's in Valencia in Spain. And so you have this cable that goes straight from the city of Valencia to the Isla de Palma. And the only thing you have to do is like to plug the DAS to power outlet, and then plug the fiber to a connector. And so then you have a laser pulse that goes down into the Mediterranean Sea. And so it's basically, it takes a couple of hours, like setting up the parameters you want, and that's it. So it's not fancy field work at all. And where DAS can really make the difference is if we have already fiber optic cable installed, then it's, as I just said, relatively easy to get access to this information. And in fact, in the ocean, there is a minimum of 1.6 millions of kilometers of fiber that have already been laid down by super large company like Google, AT&T, or other telecom companies. And so if we could reach or have access to only a very small fraction of this fiber optic cable, well, we could increase by a lot our spatial sampling and how we interrogate and monitor the Earth. One limitation, though, is that when you throw a pulse of light along the fiber, there is intrinsic attenuation, and so you cannot interrogate super long distances. Right now, the best interrogator can interrogate up to 150, maybe a little bit more kilometers, but there are also other tricks and other physical parameters that makes it impossible to interrogate very long distances. But yet, if we can just sample the first 100 kilometers, let's say, of all this cable, all the ends of this cable, that would be a dramatic increase of measurements at the ocean bottom. And so ocean bottom DAS is still relatively new. So if you have followed like the saga, the three first papers were published by the end of 2019, 2 in Nature Communication and 1 in Science. And interestingly, they were published like the same month. And interestingly as well, they were publishing very, in some way, relatively similar results. They all had their particularities, but that was interesting from an editor point of view to agree to publish the 3 papers at the same time. And since then, here there is a list of fiber optic cable at the ocean bottom or sea bottom that have been operated and for which there are papers that have been published. My point here is definitely I'm lacking other network that have been used or operated, but my point is that there is no more than maybe 20 or 25 DAS operating at the ocean bottom at the moment. So it's still relatively new, and there are many things that need to be tested and proven. And here, this slide is like just to explain a little bit what are the pros and cons of fiber optic sensing for permanent monitoring. Well, the cost per receiver is it's extremely low. If you think that with a 200 or 100 kilometer fiber, you can have, let's say, 13,000 channels. Well, the price per sensor is really low, and you have like a really high receiver density. One thing as well is that you just need like a power outlet, and if the fiber is installed, it can be there for a relatively unlimited amount of time. It's also resistant to high and low temperature, relatively high and low temperature, and also high pressure. So it's durable. And the thing is also, as I just said, it's possible to get access to all these locations we were not accessing before. But this is one pros, but at the same time, it's also a cons, because if there is no fiber optic cable for telecommunication already installed, then installing yourself a fiber, it's a multi-million dollar operation. And so right now we are trying just to get access to this telecom fiber, because otherwise it would be too expensive. And sometimes it's also difficult to get access to this cable, because of course the industry yet doesn't see like positive outputs of that. They don't see like monetary output of scientists using this fiber. So it's like a game of we have to convince them and let them understand that maybe in the future, we, the scientists, could become like a major client for their infrastructure, for early warning or earthquake early warning, for example. One thing with DAS is also it's highly sensitivity. The sensitivity of DAS is highly directional, so you only sense the strain, the axial strain along the fiber. So you don't have like a 3-component measurement. You don't have an east-west measurement. You have along the fiber component measurement. And especially at the ocean bottom, the coupling conditions are largely unknown, again, because this telecom company, they don't really care to know how the coupling is, and they don't really care either where the cable is. So they have like rough approximation, but many times it's actually really rough. And one of the main issue the DAS community is facing, and I will end actually on this, is storage. I will end this presentation on that. storage is the main issue because we can generate like terabytes per day of inflow of data. So you have to handle that. And also the laser, if you have like repeaters, as I said, the laser itself, the DAS laser cannot cross these repeaters. So if the repeater is like 50 kilometers from the shore, you cannot cross this repeater, unfortunately, unless you have like a dedicated repeater engineered for DAS measurements, which oil and gas is developing or using right now. So in the last 3 years now, what do we know? What can we do with ocean bottom fiber optic? So there are like a few papers already that showed that ocean bottom DAS or OB-DAS can record really nice microseismic signals, microseism. And in fact, we know that microseism is generated at the interaction between liquid and solid earth and near the shore especially. And so we are right there, we are right where this microseism or these microseism are generated. So the signal, if you are interested in microseism and monitoring that, the signal is generally really neat. We also know that we can record like long period signals such as current or tidal interaction. And here there is a lot of room for oceanography. In fact, with some arrays under the right conditions, the right parameters of measurement, you can retrieve like tidal change, you can retrieve ocean gravity wave, you can retrieve wave height, you can retrieve a lot of oceanic parameter outside of seismology. You can record earthquake, and that has been proven first on land, but also by the three first paper that were published in Nature and Science, and hopefully for us, so we record earthquake. You can record acoustic phase, and I will show you a few examples of that. You can also use ocean bottom DAS for seafloor imaging. And today, more specifically, I will discuss how well do we retrieve earthquakes and how can we use this earthquake to infer the site response under the array. And also how can we image the seafloor using both earthquakes and ambient nodes. So, sorry. I will discuss only about this array, which is the Sanriku array, which is an array installed in the northern part of Honshu, Japan. And in fact, this fiber optic cable serves to sustain an array of 3 ocean bottom seismometers that you have here, the white dots, and 2 pressure gauge, the little squares. And it was one of the first ocean bottom seismometer cable array installed, I think, before 2000. And after the large Tohoku-Oki earthquake, this array was partly destroyed and then reinstalled or rebuilt, and with several fiber optic cable in it. And so the Japanese decided to sample this with a DAS interrogator. And so we sampled the first 70 kilometers and at a sampling rate of 500 Hertz, a channel spacing of 5 meters, leading to an array of more than 12,000 channels. And so with only 14 days of data, it's more than 20 terabytes of data to handle. And one good thing about this array, aside that it has like ocean bottom seismometers with it, is that it's also buried under a few centimeters of sediment, 70 centimeters. And this is because Japanese law and fishery industry imposes that every infrastructure that is installed at the ocean bottom should be buried for the first, like, let's say 50 kilometers. And so this actually depends from the country to country. So sometime you will have the cable that is just laying by gravity or buried under the surface. And another good thing, of course, about this array is that it's in Japan, in one of the most seismically active parts of the world. So we were lucky enough in 14 days to record like several hundreds of earthquakes. And here I just show you, so here in this map, you only have like 106 earthquakes that we use for other studies and that have relatively good SNR, signal to noise ratio. And here is like an example of a magnitude 2.5 earthquake that happened close to the fiber, a few kilometers away only. And here we show only the first 99,000 channel. And so we can see like very clear E wave and S wave and all like many reverberation that can tell you. So now with that, we really we don't have a point measurement, but we have like a wave field measurement. We really see how this wave comes from the bottom over like a 2D grid. And one thing when you play with DAS in general and ocean bottom DAS is that the coupling is unknown, and so you need somehow to quantify it, and you would realize very quickly that some part of the array are really good and other provide like less really reliable results. In this array, we were relatively lucky that most of the array is usable, but I've seen like papers where they actually have to disregard large section of the array because the data were not high quality enough. And so here what I show you is we compute like the SNR on the A panel here in different frequency bands using the 106 earthquake I show you. And so we kind of average what is the SNR versus the channel and versus frequency, right? And so we see that for this earthquake, we have like relatively good SNR in this frequency range between, let's say, 1 and 10 hertz. And here, it's each color, it's a different earthquake of different magnitudes, and we see as well here how the SNR evolves for each earthquake along the array. And so we see that we have a big drop of SNR here. It's exactly where actually the cable passes from buried to unburied and is connected to the first pressure gauge. And then it goes up again and then start to fall down. But overall, we see that we have a decrease of SNR from the coast to the more offshore you go. And in the right image, in the right plot, what I show is, again, on A is a wave field recorded for one earthquake recorded with the DAS. And so we see clear P2S and S wave. And here it's a high net station. So one of the inland station in Japan installed in a borehole. So here we have like really neat signal, super high signal to noise ratio. One of the best signal you can expect from an instrument. And this is one of the first channel 50, which is still on land actually and not offshore. And we see that we retrieve actually relatively good data, like with high SNR, and the amplitude difference between the two, because we were able to convert to acceleration in this case, is relatively similar, although the one at the surface is amplified with respect to the one at inside the borehole, due probably to side effects near this between these two channels. And here is like another channel, you more or less here the channel 4000. So we still retrieve relatively good SNR, and so this one is buried, and this one actually the H and it's unburied. And while it starts to be unburied, you see that it's much noisier. You have like a reverberation. You have like the coda is much larger as well. The P and S wave are not that sharp. Here you have like phase water wave reverberation here. And this one is one of the OBS. And the OBS has a better signal to noise ratio, but still if we compare the two, like we retrieve same amplitude for this channel, which is right next to the OBS, we retrieve same amplitudes and same phase, more or less the same, the global phase are well retrieved in this case. So we apply as well like template matching. So we use a lot of templates from inland stations. And we run that on the DAS array in order to know how many earthquakes are we able to retrieve, like what are the detection capabilities of this array. And here you have, like in this grid, I think what's important to notice is that applying this algorithm of template matching, we were able to retrieve 100% of the magnitude 4 and higher earthquake up to a radius of 500 kilometers, and all magnitude 3 and higher for a radius of 200 kilometers. And really, that's what matters here. If we go more granular, we see that there are so little earthquake that we lose, little earthquake that we cannot retrieve. But what matters for us and for earthquake early warning is like the relatively high magnitude earthquake. And so this is very promising to say that all magnitude 3 and higher earthquake can be detected relatively easily with DAS. And we detected other type of signals. And actually, I put these slides here because I have, to be honest, I don't know what it is. We retrieved this signal, which is super short in time. It's like a little bit more than 1 second. And it repeats like many times over the 2 weeks. It happens like in a set of channels, like a few hundreds of channels in this region, so near the coast. And we have found that signal like thousands of times. It's probably not an earthquake. And why it's probably not an earthquake? Because it peaks on Sunday afternoon. So it has probably an anthropological origin, but yet we haven't been able to find out. So if any one of you has any idea, that's why I put this slide. I'm still curious to know any idea that you may have. And also one thing to recognize is that, so the coupling between the ground and the cable, it's a node, but these sediments are mushy, really rich in sediment, in water, sorry. And so the coupling between the water and the cable is actually excellent. And for this, then we can retrieve really neat acoustic phase. And actually it has been developed for that at the beginning. No, it's an acoustic sensor. So here, for example, I show you like one T phase, so tertiary phase that has been recorded all over the array. So here from about 5 kilometers from the coast until like 60 kilometers. So down more than 1,000 meters deep. And so I was scratching my head for a long time. So when you have a T phase, you need to have like an elastic phase first. Now you need a PNS and you need an earthquake. And so then part of the energy is released into the water level. And then it can actually propagate over large distance because acoustic phases are poorly attenuated in the SOFAR channel in some region of the ocean. And so I was looking what triggered this T phase, or where is the source? And after like several hours of looking and looking, I realized that the only match, if I compute like the travel time of the T phase over a given distance for a given earthquake, the only match was a magnitude 4.5 earthquake in Chile. And that was the only match. So I was like, that sounds like a little bit too far, no? So it's like more than 16,000 kilometers away. So I looked at one station in Hawaii, which is almost on the beach, so really close to the water level. And I compute like the exact same time, okay, what would be the time of this T phase to arrive at the station in Hawaii? And boom, I retrieved the exact same T phase. So that was like encouraging, telling me, okay, so it's likely that it's actually coming from this earthquake in Chile. And so I've been looking for reports or other papers where they document T phase, and I've never seen such T phase coming from such a large distance. And in fact, in the SOFAR channel, when you have like a T phase propagating, it's acting like a fiber optic. You have, so the SOFAR channel is a region inside the ocean where the velocity of the wave is slower, acoustic wave. And so it starts like to reverberating inside this SOFAR channel with very low attenuation, and it can actually propagate over extremely long distances. And so then we start looking for other T-phase, and actually there are a lot in the data set. So there is room also to study the structure of the water and things like that using these phases. And now let's go to another part of this talk about like site response analysis. So when you have like sedimentary sites, so here it's one KickNet station in Japan, where you have a station in the borehole and a station at the surface. And as we have seen with the DAS array, the station at the borehole has like lower amplitude than the one at the surface. And that's because of site effect. You have like amplification of the wave when they are recorded near the surface. And this, so you can compute that by doing like a spectral ratio of these two, and you can see which frequencies are amplified or not between by doing the ratio between the surface over the borehole channel. And if you repeat that for several earthquakes, you normally should retrieve always the same information, always the same curve, the same site response curve. And if it's always the same, it means that the sediment layer interact linearly somehow. No, there is no change through time. But when you have like very strong ground motion, such as the large 2011 Tohoku-Oki event, and you do the same analysis, you see that you may have like a change of this curve. And so in fact, what happened, it's you may have like a de-amplification or a damping or a compaction of the rapid compaction of the sediments. And so that will shift this curve, this H over V curve. And so that means that you, during this earthquake, you have had a nonlinear response of the soil. And in the worst case scenario, this nonlinear response can lead to, for example, liquefaction. And here I show you like two images for the Christchurch event and Yagata earthquake in '64, where actually liquefaction happened. And liquefaction is really a local thing. So here you see like this car there. I don't think you see my point, by the way. No? Not sure. Anyway, so you see that there is a car like in the driveway, and there is one car like sinking, and they're like a few meters apart. And so it's really hard to have good information on what are the site effects on a very local scale. And so that's where DAS could potentially help. So because DAS, with this array, we have one channel every 5 meters. So we can potentially like start analyzing what is the site response. Does it act linearly or non-linearly every 5 meters? And so better predict site effect response. So for this, what we did, we used the same set of 106 earthquake, and we applied like autocorrelation function, autocorrelation processing, so which is known to represent the reflectivity response of the ground. So either for the P or the S wave, when you do the cross correlation, you can retrieve like a wave that bounces up and back, so the transfer response from between the channel at one given channel. Sorry. And here what we did, so we have all this earthquake 106, and we compute the autocorrelation function in many different frequency bands using the S wave. So here we have like a given frequency bands, we retrieve an autocorrelation function for one earthquake, same earthquake, but other frequency band, we retrieve another autocorrelation, same earthquake, but another frequency band, higher frequency, 15 to 30, and we retrieve another autocorrelation. And then we sort out all these autocorrelation function for all the earthquakes, sorted and ranked in peak strain, in their peak strain that we measure. And if we take like a reference cross correlation for all of them, and we kind of slice that through all the cross correlation we have, we can see that when the peak strain is like under 80 in this case, there is no change in the medium. But then for strong ground motion, we see that there is a little change. And by looking at the difference between the reference curve cross-correlation and all these individual autocorrelation, we can infer the change somehow in the medium and how this medium is behaving. And so this is kind of a complicated plot because here I show you at one given frequency, right? 12 to 24. But this is the same plot, but for all frequencies that we have computed. And computed for all the earthquake as well. So you have like a dynamic peak strain measured, and then a central frequency of all these filters. So we have all the earthquakes for all the different frequencies at a range of stations. And so we see here, when we are in green, there is no change in the properties of the medium. So at low peak strain, we don't see any nonlinear behavior. However, at higher peak strain, at certain frequencies, we do start to see nonlinear behavior. And we can do that at many places over the array, and we did that for the entire array. And so we can see actually that this change both, it changed in frequency and spatial. So, and here, for example, another set of stations where we do not see almost no nonlinear effect where we are like closer from the coast. So here, this is just to show you that DAS can be used for analyzing precise site effect and nonlinear response of the ground. And now I want to go quickly over this, like how to image the seafloor using DAS. So here we realize actually in this earthquake and one other I showed you earlier, that there are a lot of ringings of this wave here, right? So here this is the S wave, and we have all these wave packets that arrive right after the S wave. And these, in fact, are Scotty waves, so surface interface ocean bottom. And so if we develop like an algorithm to automatically extract this surface wave, because now we can think about that. So we have one earthquake, but in 2D, so we have a wave field. And so we observe that we have like surface wave everywhere that are generated. And so we can extract them, we can compute a dispersion curve, and with this dispersion curve have an idea of the velocity model under a given set of station, no? And so we did that for one earthquake, but also for many different earthquakes. I think we had in this, we had more like than 30 earthquakes with good signal to noise ratio. And so we can extract automatically all these surface waves in the earthquake wave field and invert velocity model using this. And so the question we had as well is, why do we have so many surface wave and in these records? And so I just want to show you here some synthetics. So in scenario A, you have like an earthquake source with all the rays that the scenario A is the one that we are used to see, right? So where you have like propagation of the energy in all the medium in the earth and then in the water column. And then you have reverberation of the water column. And so you have still, again, energy that comes back to the earth. And in scenario B, we did the same, but we cancel all water reverberation. Okay, every time there is a water, so this is, we put the water as an absorbing boundary. That's the only thing that we change in our model. And in scenario C, we subtract B from C. And so we keep, in that case, only the energy that comes back from the water reverberation. Okay, so normally it was supposed to start. Let's look at the first one. So here, this is like the classical scenario where you see all this reverberation, right? And you see like this bouncing. In this case, it's kind of, in B, it's kind of weird because you see you have like an absorbing boundary, right? So it just goes and never come back. And then in C is the subtraction of the two, the difference between the two. And so here we just see the energy that comes back from the water reverberation. And so here we can emphasize that in fact, you have a lot of energy that is kind of trapped in the water column and continue to reverberate between the two constantly, and sometimes for several minutes, right? And in fact, we think that what we have seen, all these little surface waves, it's due to water phase reverberation. So you first have the S wave coming, and then you have like this bouncing of the energy inside the water column. And every time the energy or the wavefront, the acoustic wavefront touch the ground again, perpendicularly to the ground, you have like a little blast of energy. And that's actually, you can see, generate like this surface wave that travel. Every time you have like surface wave that travel horizontally here in this medium. And then I guess many of you have worked or are working on ambient noise and ambient noise cross correlation. And what is nice with PubDAS is you are at the source of the ambient noise. No? This is where the ambient noise is mainly generated. So we applied traditional ambient noise processing, and here is like what we get. So for a given set of station, we retrieve like the surface wave between the station. We can transform that in the phase velocity domain, and so see how the energy of this wave propagates in terms of modes. Here, in this case, we observed Rayleigh waves and higher modes of Rayleigh wave. And we were quite surprised by the number of modes that we can actually retrieve. It's just, for some station, we have like a gigantic amount of modes. And with DAS now, we have so many stations, one station every 5 meters, so we can start playing with the best geometry that we want. Do we want one station every 5 meters? Do we want one station every 20 meters? Do we want 200 receivers or 500 receivers? And so you can actually, by playing with all these parameters, you can separate more or less the modes and target different region of the medium. So here I show you different number of receivers, but always with the star being like the center of our array. So we are sampling more or less the same medium, and we see that the more station we take, the more separated are these modes. And here just now, I show you different like dispersion curves analysis. So phase velocity versus frequency at different places along the array. So we have like 1500, it's one channel which is close to the shore, and 8000 is like further away from the shore. And so in some of these, we see that there are like up to 50 modes, which was quite remarkable. Honestly, I never saw that before. And in other one, we only retrieve like barely 2 or 3, and with these horizontal lines here. And we realized that these, not horizontal, these diagonal lines here. And these diagonal lines, in fact, they are due to spatial aliasing, and there you can control that. And we have published that in the paper. There is an equation that I'm not showing here, but basically based on the number of channel you take and the space between the channel, you can control more or less if you retrieve, the aliasing will be dominant in your cross correlation or not. But there is complicated factor between the two, because there is sometimes the structure is such that it can overcome the aliasing. In our case, we have realized with synthetics that I'm not showing here, but if you have a very low gradient of the velocity, that can actually overcome your aliasing as well. So you have both like processing on one side and the structure itself that can interfere with your analysis. And so this is like the results. And so we have, I think, one velocity model every 50 meters or 100 meters. And so we could have been more granular because we have one station every 5 meters, but that was a choice that we did at the beginning. And so, but it's still nice. We still have like a very high resolution for surface. So this is VS, and we can retrieve like these zones of low velocities, zone with higher velocities at deeper depth. And the fact as well that we invert so many modes, we are sensitive to many different depths, so we can constrain the depth as well. And so as a conclusion, right, I would say PubDAS is fun. There are like a lot of room for you to develop whatever you want, basically. There are room for oceanography, for port monitoring, earthquake source characterization, ambient noise studies. As I said, you are like at the heart of the ambient noise, early warning, earthquake early warning. Some people monitor mammals and whales using DAS. There are a lot of engineering application as well. But one issue is that DAS is not for everyone right now. So it's costly. The instruments are quite expensive. There is no instrument pool, such as from Pascal in the US, where scientists can just request, let's say, 200 nodes seismometer for an experiment. There is no pool of instrument of DAS. And there is no data sharing platform. Because of the storage issue, because the amount of data is so great, platform like Iris cannot accept the current inflow of data. And so there is many scientists in the world that would like to be involved into the DAS research, but right now only rich universities or industry can afford to purchase an interrogator, and when they have data, they cannot share them with the public. So we are like in a bottleneck where only a few group of researchers can develop DAS research. And so to face that, we have developed a repository called PubDAS, Public DAS Repository, where we host more than 100 terabytes of data from up to 8 data sets, and which is hosted here at University of Michigan. And so we have here a little bit of everything. We have like ocean bottom DAS, we have inland, in cities, in desert. We have active sources as well. We even have like a permafrost tow monitoring. So there are many things that could be done, and many of these DAS arrays haven't been like explored in many details as well. So there is really a lot of room for improvement. And actually right now, like in 10 minutes or in 15 minutes, I will give another talk just on PubDAS. It's led by the DAS RCN community here in the US. So if you are interested to know how to download this data, I will give like a 10-15 minutes talk, like in half an hour from now, but the other conference starts like in 10 minutes. So yeah, and we have still some time for questions.